Have you ever noticed how your desk seems to get messy all by itself? Papers pile up, pens roll around. It's almost as if there's an invisible force at work, turning your once organized space into a chaotic mess. It's like the universe conspires to create chaos on your workspace. No matter how often you tidy up, the clutter seems to return. Well, there's a scientific reason for this tendency towards disorder. It's called entropy. Entropy is a concept from the second law of thermodynamics, which states that the total entropy of an isolated system can never decrease over time. Essentially, entropy measures the amount of disorder or randomness in a system. The higher the entropy, the more disordered the system is. Think of it this way: a neat and tidy desk has low entropy. Everything is in its place and there's a sense of order and organization. A messy desk, on the other hand, has high entropy. Items are scattered everywhere and there's no clear organization. Entropy is a concept that applies to all aspects of life and the universe. Welcome, science fans. Scientists study entropy to understand how systems evolve over time. By examining the changes in entropy, they can predict how a system will behave in the future. On a cosmic scale, entropy plays a crucial role in the evolution of the universe. As the universe expands, the overall entropy increases, leading to more disorder and randomness. Embrace the chaos and appreciate the beauty of entropy in our everyday lives. It's a reminder that change is constant and that disorder is a natural part of the universe's grand design. Entropy is all around us. It's a fundamental concept in physics and chemistry that describes the natural tendency of systems to move towards disorder. This principle is not just confined to scientific theories, it manifests in our everyday lives. It's also why it's easier to break something than to put it back together. When a vase shatters, the pieces scatter in a disordered fashion. Reassembling it to its original state requires effort and precision, highlighting the natural drift towards disorder. In simple terms, things naturally tend to become more disordered over time, requiring deliberate action to restore order. This tendency towards disorder is a universal phenomenon. But why does this happen? Why do systems naturally evolve towards higher entropy? To understand this, we need to delve deeper into the concept of probability and the nature of spontaneous processes. Imagine a deck of cards neatly stacked in order. This represents low entropy. Now shuffle the deck. The cards are now in a random order, representing high entropy. Similarly, you have a perfectly ordered deck of cards. Each card is in its designated place, creating a sense of order and structure. Now, you drop the deck on the floor. The cards scatter in all directions, creating a chaotic mess. What are the chances they'll land in perfect order again? Pretty slim, right? The likelihood of the cards returning to their original ordered state is extremely low. There are countless ways the cards could be arranged randomly. Each random arrangement represents a state of higher entropy compared to the single ordered arrangement. There's only one way for them to be in perfect order. This singular state of order is vastly outnumbered by the multitude of disordered states. Scientists call processes that increase entropy spontaneous processes. These are natural occurrences that don't require external energy to proceed. These are processes that happen naturally without any outside help. Think about a ball rolling downhill. It moves effortlessly, driven by the force of gravity. It doesn't need a push to go down. The natural inclination is for the ball to move from a state of higher potential energy to lower potential energy. Gravity takes care of that. This is a simple analogy to understand how systems tend towards higher entropy, because it's simply more probable. The number of disordered states far exceeds the number of ordered states, making disorder the more likely outcome. Why does it roll down and not up? It's all about energy. The ball has more potential energy at the top of the hill. As it rolls down, this potential energy is converted into kinetic energy, the energy of motion. The ball wants to be in a lower energy state. The bottom of the hill represents a lower energy state than the top, so the ball naturally rolls down to reach that lower energy level. Entropy and energy are related. Systems tend towards states of higher entropy because these states typically have lower energy. It's like the universe is lazy. It wants to be in the lowest energy state possible. This model helps us understand why many processes are spontaneous. They happen because they lead to a decrease in energy and an increase in entropy. Are you enjoying the video? Subscribe so that you ace that chemistry class. See you in the next video, and good luck. Let's solve a thermodynamic problem involving the calculation of enthalpy change dH, entropy change ds, and Gibbs free energy change dg for a chemical reaction. Here's a breakdown of each part of the solution. The reaction given is 2CH3OH L plus 3O2 G, 2CO2 G plus 4H2O L. The goal is to calculate dH, ds, and dg for this reaction at 25C, 298.15 K to determine if it is favorable, spontaneous, or unfavorable. You should receive a list, sometimes within the problem, for the standard enthalpies of formation, DHF, and standard entropies, S for each compound. Here are the values for the following set of molecules: CO2, G, DHF equal sign 393, 5 kJ/mol, S equal sign 213.7 J/mol K, H2O, L, DHF equal sign 285, 8 kJ/mol, SA 69, 95 J/mol K, O2, G, DHF equal sign 0, S equal sign 205 J/mol K, CH3OH, L, DHF equal sign 238, 7 kJ/mol, S equal sign 126.8 J/mol K. Use the formula for the standard enthalpy change, DH equal sign products, reactants. For products, 2x393, 5 plus 4x285, 8 equal sign 1930, 2 kJ/mol. For reactants, 2x238, 7 plus 3xe equal sign 477, 4 kJ/mol. Calculate dH equal sign 1930, 2 477.4 equal sign 114.52, 8 kJ/mol. Since DH is negative, the reaction is exothermic, which means the reaction is spontaneous. Use the formula for the standard entropy change, DS equals sign products, reactants. For products, 2x213, 7 plus 4x69, 95 equals sign 707.2 J/mol K. For reactants, 3x205 plus 2 8 equals sign 868.6 J/mol K. Calculate DS equals sign 707.2, 868.6 equals sign 161, 4 J/mol K. The formula for Gibbs free energy change, dg equals sign dH, TDS, substitute the values converting ds to kj by dividing by 1000, dg equals sign 1452, 8, 298, 15ths, neuro, 1614, equals sign 1404, 7 kj/mol. Since dg is negative, 1404, 7 kj/mol. The answer is 1404, 7 kj/mol. The reaction is favorable spontaneous at 25C. Make sure to pause the video if this didn't make any sense. Next, let's solve a Gibbs free energy calculation problem for a chemical reaction. Here's a breakdown of the steps shown. The reaction being analyzed is N2G plus 3H2 G, 2NH3 G. The goal is to calculate dGRXN at 25C, 298.15 K, using enthalpy DH and entropy DS values. Standard enthalpies of formation, DHF, and standard entropies, S for each compound. Use the enthalpy change formula, DH equals sign products, reactants. For products, 2x45, 90, equal sign 91, 8 kJ/mol. For reactants, 0 plus 0 equals sign 0 kJ/mol. Calculate DH equals sign 91, 8, 0 equals sign 91, 8 kJ/mol. Use the entropy change formula, DS equals sign products, reactants. For products, 2 7 equals sign 385.4 J/mol K. For reactants, 38130, 6 plus 191.6 equals sign 583.4 J/mol K. Calculate DS equals sign 385.4, 583.4 equals sign 198 J/mol K equals sign 0, 198 kJ/mol K. Note, this result was converted to kJ for consistency with DH in the next calculation. Formula for Gibbs free energy change, dg equals sign dH, TDS, substitute the values, dg equals sign 8, 298, 15x3, 198, equals sign 32, 8 kJ. Since dg is negative, 8 kJ. The reaction is favorable spontaneous at 25C. Model 2, from gas to salt, how order arises, occasionally. From time to time, the system can become more ordered. How do you explain that? It's a great question, and one that has puzzled scientists and thinkers for centuries. The universe is a complex place, and while it often seems like everything is moving towards chaos, there are fascinating instances where order emerges from disorder. You're right. Not everything in the universe is constantly becoming messier. Sometimes order arises from disorder, but even in these cases, entropy plays a crucial role. Think about cleaning your room. Initially, it might be a chaotic mess, but with effort, you can organize it. However, this effort requires energy, and in the process, you might generate heat or use up calories, contributing to the overall entropy. Similarly, take the example of sodium chloride, or NaSal, the scientific name for table salt. This simple compound is a perfect illustration of how order can arise from disorder in nature. Imagine you have sodium ions, Na+, and chloride ions, Cl, floating around as gases. In this state, the ions are free to move about randomly, and their arrangement is highly disordered. So, these ions are highly disordered. They have high entropy. Entropy, in simple terms, is a measure of disorder or randomness in a system. The more disordered the system, the higher its entropy. When these ions come together to form a salt crystal, they become highly ordered. This process is fascinating because it shows how nature can spontaneously create order from chaos. The crystal has a very specific repeating structure. Each sodium ion is surrounded by 6 chloride ions, and each chloride ion is surrounded by 6 sodium ions, creating a stable, orderly lattice. It seems like entropy has decreased, right? The ions have gone from a high entropy disordered state to a low entropy ordered state. But there's more to the story. Well, here's the catch. When the ions come together, they release energy in the form of heat. This process is exothermic, meaning it releases energy to the surroundings. This release of heat increases the entropy of the surroundings. The energy released as heat spreads out, increasing the disorder or entropy of the environment around the forming crystal. So, even though the entropy of the salt crystal decreases, the overall entropy of the universe still increases. This is a fundamental principle of thermodynamics. The total entropy of an isolated system can never decrease over time. It can stay the same in ideal cases, but it usually increases. This is why, even when we see local decreases in entropy, like the formation of a salt crystal, the overall entropy of the universe continues to rise. It's a beautiful balance that keeps our universe in check. Chemical reactions and entropy. Why ice melts. Take melting ice, for example. When you place an ice cube in a glass of water, it starts to melt. Ice is a structured, ordered arrangement of water molecules. The molecules are tightly packed in a regular pattern. When ice melts, those molecules become more disordered. They spread out and move more freely in the liquid state. This transition from a solid to a liquid increases the entropy of the system. This means the entropy of the system increases. The once orderly arrangement of molecules in the ice becomes a more random and disordered arrangement in the water. Let's dive a little deeper into why that happens. When ice melts, the water molecules go from a highly ordered crystalline structure to a more disordered liquid state. This means the entropy of the water molecules increases. But wait, there's more. Melting also requires energy. The heat absorbed by the ice causes the water molecules to vibrate faster and break free from their rigid structure. For example, ice melting into water is a spontaneous process driven by the increase in entropy. So why does ice melt spontaneously at room temperature? It's because the increase in entropy of the water molecules outweighs the energy required to break the bonds in the ice. The universe favors the state with higher entropy. In our daily lives, we are constantly battling against disorder. From organizing our schedules to cleaning our homes, we are in a perpetual state of creating order out of chaos. This struggle is a manifestation of the natural tendency towards increasing entropy. But entropy isn't just about disorder. It also drives many essential processes in living organisms. Your body breaks down complex molecules in your food into simpler ones, a process that increases entropy. Yet this breakdown releases the energy your cells need to function, grow, and repair. Life, in its essence, is a delicate balance between order and disorder, constantly harnessing energy to maintain structure while inevitably contributing to the universe's overall entropy. So next time you find yourself tidying up or noticing the cycles of nature, remember that you're witnessing the profound influence of entropy at work. It's a beautiful reminder of the intricate dance between chaos and order that shapes our world. Thank you for watching. If you enjoyed this video, please like, share, and subscribe for more content on fascinating topics like entropy and beyond. Stay curious. Be sure to have a nice night, and good night.